Good afternoon, everyone. Welcome to our happy post-launch press conference for Juno and the Atlas V rocket launched earlier in the afternoon. Here to talk about the mission and the status of the Juno spacecraft is Jim Adams, the Deputy Director for the Planetary Science Division at NASA headquarters in Washington. Scott Bolton, the Juno Principal Investigator from the Southwest Research Institute. And Jan Chodas, the Juno Project Manager from the Jet Propulsion Laboratory. And we'll begin first with Jim Adams. Jim?
Well, thanks, George. It was a great day for a launch, and we're extremely happy that the weather cooperated with us and Tropical Storm Emily dissipated in the Caribbean. We're at NASA headquarters. We're extremely proud of the Juno team entering the launch phase of this, our year of the solar system. And we're looking forward to just some fantastic science in roughly 5 years' time. I think the team should be commended for delivering this mission on cost and on schedule in an environment that is extremely difficult, and the expectations of the team were very high. And so I convey my thanks to everybody who was involved in the Juno effort, and we look forward to the science that we're going to get back here in 2016, right, Scott? Take it over.
Yeah, 2016. In fact, next stop is Jupiter. We arrived there July 4th on 2016. Go into orbit there, polar orbit, and start to unlock those secrets of Jupiter that we've been trying to get at for a long time. I can't be happier. I mean, I could not be happier than this. It's sort of like a dream come true. You know, more than 10 years ago, we had these ideas. And then, you know, yesterday, looking at that rocket, I realized, really starting to put together that this is happening. There's the spacecrafts inside the rocket, and we're about to leave. And today we left. And we're on our way. And, you know, at this point, the spacecraft's out. It's open. The solar arrays are open. We're flowing our electricity through the veins of Juno. And we're on our way and getting ready now to gather all the great science and get everything working. And it's just really a thrill. It's exciting. It's a relief because there's some tension associated with this, of course. But I'm happy that everything worked on schedule, and you know, we're on budget, on schedule, and we launched on the first day. The whole story is consistent, so I'm happy. And Jan will give you some details of exactly what's going on with the spacecraft right now.
Thanks, Scott. Well, this is certainly a wonderful day for the Juno team. We had planned for this day for many years. Everything clicked off like clockwork today. We didn't launch at the opening of the window, but we had planned to have our 69-minute window here today to allow for things to check out at the last minute, make sure everything was on track, ready to go. We lifted off at 12:25 p.m. Eastern Daylight Time. We separated 53 minutes later, so about 1:18 p.m. Eastern Daylight Time. The launch vehicle left us off at the nominal attitude, right where we wanted to be. The launch vehicle folks did a fantastic job, gave us a great ride. And the Deep Space Network was amazing. Perth had acquired us. That's the ESA station that we had for downlink recording at 1:18:30, 24 seconds after we separated from the Centaur upper stage. The Canberra DSS-34 station locked up with us at 1:18:45, 39 seconds to lock up after separation, which is just a phenomenal statistic from the Deep Space Network. Couldn't be happier with that. We started our solar array deployment about 5 minutes later as planned. The arrays deployed properly. We spun down to 0.4 RPM as predicted, right on the dot, and then the spacecraft spun us back up to 1 RPM as planned. We were left off about 19 degrees off sun within the 20-degree cone that we needed, so we did not need to turn to put the arrays on the sun. We were already pointed in the right direction. So everything was, our favorite word, nominal. We also, on my way over here, I got a call saying that we had sent in our first command. We sent a no-op command that doesn't do anything, just proves that we do have commandability. So I'm happy to say that we are stable, we are spinning, we are power positive. The arrays are picking up power and recharging the battery, and we're commandable. And so those are the 4 things that we wanted today. Couldn't be happier. The other thing I was going to note was our batteries only discharged to 90% during the ascent, so they gave us a phenomenal performance during that time. And in fact, they didn't have to work that long because they were good for 6 plus hours after separation, and we got off on the solar arrays within minutes. So thank you to the extended Juno team, our KSC and launch vehicle friends, the science community that we were eager to do this for. It was just a team effort from start to finish. I'm really looking forward to a great ops ride.
Thank you, Jan. And we'll take questions now. Please give your name and affiliation when the microphone comes to you, and we'll start here in the front with Marcia.
Marcia Dunn, Associated Press, probably for Mr. Adams and maybe Dr. Bolton too, but today of all days people are worried about money. And I'm just wondering, $1 billion I know is on cost, but can you just sort of say why you guys think that this is going to be money well spent?
I'll go first, and then Scott can correct me. No, actually, you know, exploring the solar system is all about finding our place in the universe. And there is something about exploration that strokes the spirit of every person. And so I believe that unlocking the mysteries of how we got here is a fundamental question that if everybody would pause and think about for a moment, they would find is something that's deep within them. And I believe that it's worth the money to go find out the answers to these questions. You want to add to any of that?
I think you said it pretty well. I mean, I think, you know, searching for our origin and understanding the fundamentals of nature is something that all societies should be trying to do. And of course, the more successful your society is, the more you can afford to go after these really fundamental questions that are so important. And that's really how you progress. Technologically, that's how you progress philosophically. You have to learn about ourselves, and these investments are really in ourselves, and I believe they're worth it. The other thing about, you know, $1 billion is a lot of money, but if you think about what we're doing with Juno, we've got incredibly sophisticated instruments, some of the most advanced that have ever been on any spacecraft at all, and we're going into orbit around Jupiter with these. So traditionally, these things are even more expensive, and we've really designed something through the synergy of the engineers and the managers and the scientists together to do it even more efficiently than it's ever been done before. So I think we're showing that you can even get more done for the money.
Okay, Stefano.
Yes, thank you. Stefano Colodano for Italian Radio and TV. Excuse me, what is the current speed of the spacecraft, if you know?
I don't know.
Or at separation?
We'll probably have to get that.
Oh, yeah, we'll have to get back to you. I'm not sure if it's in the press kit or not, but you're asking at separation, what was our velocity?
The only thing I can tell you is it's greater than the escape velocity of the Earth. But I don't know that exact number, but I'll bet you one of our guys can get that to you.
Okay, question right here.
Leo Enright with Irish Television. I was wondering what an average day at the office is going to look like for the flight control team for the next 5 years. I mean, is there a room where people will gather every day to control this spacecraft, or do they just come to it once a week, or can they do it, you know, from their sofa at home with an internet connection? Or, you know, could you talk just briefly, how does it look when you're in a coast for this length?
Well, it's not 5 years of boredom, that's for sure. At first, what we'll do is monitor the spacecraft around the clock, because we want it's a brand new baby, we want to make sure that we learn to understand and appreciate its quirks and idiosyncrasies. So we want to monitor it carefully. When we feel comfortable, and so we have DSN passes around the clock. When we feel comfortable that we can, we'll probably give up on the night shift first, and we'll back off a little bit. We do have a maneuver planned at 20 days, which may or may not be needed depending on how the launch vehicle performed, and we should know that within a week. We'll know whether we need to do that maneuver or not. But we were left off in such a great place from the launch vehicle. I'll place my bets when I get home. Then we'll move into characterizing the instruments. So we'll get to know the engineering subsystems first, and then we'll do the low voltage checkouts of the instruments and the high voltage checkouts of the 3 instruments that operate at high voltage. That'll take through about December. Then we have our 2 deep space maneuvers about a year after launch, September 2012 timeframe. We start our DSM preparation campaign, as we call it, in about the February timeframe. We want to make sure that we dot the I's and cross the T's, take that design down to the nth level, have the right peer level reviews, independent reviews to make sure that we're not missing something. And so the team will decrease in size because we'll have a larger staff at the start. We carry some of the development folks into operations to make sure that we benefit from their knowledge and we don't miss anything as we make the transition into a more of a steady state operations. So we'll work on that DSM preparation, and then the months fly by pretty quickly when you're doing something like that, and then a year later we have the Earth flyby, October 2013. So and we'll do the same sort of preparation campaign several months ahead of time using the Earth flyby appropriately as a practice run for what we're going to do on one of our passes at Jupiter. Then when we go out into the quiet cruise, I believe we will have some downtime. Shortly after launch, we'll get down to the 2 tracks a day, and then we'll get down to the 2 tracks a week and 1 track a week. Then it'll go up and down depending on the activities that we have on board and how often, when we're doing the instrument checkouts, for example, we'll have more passes. In the quiet cruise, we'll be down to about once a week, but people do meet daily. We'll have daily status meetings for several months. It's a very tactical operation at this point. We like the team to come in to do to have those technical meetings and make sure we have the tag up, but we have a distributed team. The spacecraft team is flying it out of Denver, and so we have all the modern conveniences of internet, video conferencing, teleconferencing that we've used during our development, and we'll continue to do that. And then of course we have the whole science community. We want the scientists to come and reside with us at JPL during the checkouts, but then they'll be back at their institutions. We've already proven out that we can flow the data end to end all the way out to their institutions. They can use their familiar equipment and be at their home institutions when they get their data. So it'll really, the tempo will vary from the start of the mission as we progress.
Bill?
Bill Harwood, CBS. Well, Janice sort of answered my question too, but just maybe a little follow on. Sometimes these flights, deep space missions, there's still software development required and you're still working on the science plan during transit. Is this a mission where you pretty well know what you're going to do when you get there, or are you still refining how you're going to go about it?
As far as the flight software that's residing in the onboard processor from the engineering perspective, we have no post-launch development planned. We have already designed and tested our JOI sequence. That's not to say that we won't do, we'll dust off those notebooks when we get close. We'll run that again. We'll make sure that anything that we've learned from the behavior of the spacecraft will modify the sequence as appropriate. But I would consider that more part of normal business. I'll let Scott talk about the science planning because some of it's done to a certain level and others will continue to refine.
To a large scale, we have the science plan figured out and we kind of know what we're going to do. And in fact, that's one of the reasons that this mission is so efficient, is that we've designed it in a way to just gather the data with little detailed planning, unlike some of the other types of missions that go. But we still haven't built the sequences for what would actually be run at Jupiter, so we will have to do that, and there will be some choices that can be made, and some of those choices will wait to see how the instruments are functioning and the idiosyncrasies that Jan mentioned earlier when we go through all the calibrations and we go through how and learn how the instruments work and exactly how well the measurements are that we can predict, then we will refine our plan a little bit. But to a large scale, we have our plan already figured out. When we go into orbit, we know pretty much where we're going to get what measurement.
And just one quick follow-on. I think you guys addressed this at one of the pre-launch, and I can't remember what the answer was. When you guys do the flyby, are you going to be taking any imagery or science? I mean, when's the first time we're going to see any pictures out of this?
Earth, you mean?
Yeah.
The Earth
when
flyby?
are we going to see pictures for the first time out of your instruments? That's what I'm looking for.
Well, I can't tell you that when the first day that we'll get an image down of anything, because we may accelerate that plan from what we have right now, depending on how things work. But right now, we plan to operate most of the instruments at the Earth. One, to learn how they operate and make sure that we understand how a sequence that we would actually operate near Jupiter will work. Sort of an example. In previous missions that have gone to the outer planets, that have had Earth flybys, you know, it's really dictated by the energy and the fact that you need to go around in order to get out to the outer planet. You made incredible use of the fact that you went by the Earth, not only to calibrate your instruments, but to also get new science, but maybe most importantly, you learn about the spacecraft long before you get to the outer planet when you're going there so that you can adapt your plan if needed. So we will make use of all of those things. We will be limited by the fact that some instruments we will have to analyze and make sure that thermally, this close to the sun, since they're designed to operate at the Jupiter, that we aren't taking any risks. That will be our first priority. And then the calibrations that are unique at Earth will also be the second priority. And then the third will be whatever new science we can possibly get.
Okay, a question right here in the back.
Mark Ratterman from Talking Space. Question for Scott Bolton. Do you think that our educators that are teaching our middle school, high school children, do you think that they'll be having some exciting things to talk about after Juno enters orbit, or will they have some things to talk to their kids about beforehand?
Well, I hope they have exciting things to talk about beforehand, even right now, because there are exciting things. I assume you mean just respect to Juno, though. Not all science, but there will be some things that they can talk about. A lot of them are technological stuff, advances that we've made with solar arrays, the radiation vault, things that are unique to Juno, the challenges that have gone on, I think help teach kids that might be interested in engineering. And the science that's coming is lessons that we've already started to incorporate in curriculum for those grade levels. And in fact, we're trying to push it down to elementary school. Now, of course, once we get to Jupiter and we learn the new things that Juno is going to learn for us, that will open up, you know, a wealth of new information that will provide it. And so, you know, that may dwarf what we've been able to do prior to that, at least with respect to Juno.
Okay, let's come up here to the front to Ken Kramer.
Hi, Ken Kramer for Spaceflight Magazine. For Scott Bolton, please. I wonder if you could tell us a little bit about how this idea originated in your mind, the kernel of the idea, when you came up with it, how it might have evolved. Is it every bit that you wanted? This you know, the idea for the mission, did it evolve over time with the instruments, or what?
It did. Some instrument ideas might have been like a revelation. Other ones have evolved over time. It started long before I was a kid, when the first scientists were trying to go into polar orbit around Jupiter. In fact, even in the 70s, people were arguing as we started to plan Galileo that maybe that kind of a mission should be a polar orbiter. Most of those studies were aimed at trying to understand the polar magnetosphere, although some of them understood that if you could go into polar orbit, you might be able to get better measurements of the magnetic and gravity field. And then in the late 80s and 90s, there were missions that were conceived of to go into close orbits, near polar, not truly polar, but highly inclined orbits, similar to Juno's, to look at the magnetic field and the gravity field. And those, one of those was called Inside Jupiter, and it progressed and tried to win. It was also proposed competitively and didn't make it all the way to the final round. And then about the time Cassini was flying by Jupiter, I was on the Cassini team on a few instruments as a co-investigator, and was arguing that we should do science at Jupiter as we flew by. And I was able to persuade enough people that opened the door, but I was also tasked with figuring out which science we should do. So a colleague of mine and myself ran workshops to try to figure out the science that we could do by going by Cassini. And one of those experiments that I came up with was to borrow the radar antenna. It also uses the high gain antenna on Cassini, and map Jupiter's radiation belts because it could work in a listen-only mode. It was an instrument that was primarily designed to see through the clouds of Titan and map out Titan's surface, which was incredibly high priority also for Cassini. And I was very familiar with that because I was also working to figure out what we should do at Titan, so I knew how that instrument worked pretty well. And so we borrowed this thing, and I suggested that we make a map of these high-energy radiation belts, which was part of the science that I had done before. And that got approved, and one of my other co-investigators came up and said, you know, can you use that to figure out the water abundance inside Jupiter? And I said, no, I don't think so. And we worked out some details, and then the next day I was, you know, getting ready to work and literally in the shower. And I realized, gosh, I was looking for water, and there I was. And I realized, gosh, if we got a bunch of these antennas in the right place over the poles, I could get away from the noise of the radiation belts and see into the planet, and maybe make that measurement that my colleague had asked for. And so I came back in the next day kind of excited, saying, I think I figured out a way to do this, but not with Cassini. And we don't have anything that can do it. But I think if you made something like this, it might work. And that colleague of mine was named Toby Owen. And he went and got a colleague of his named Daniel Gautier. And they came in and tried to argue with me on why that was so important to do and how fundamental that measurement would be. And they were saying it was could be the basis of a mission. And I had my doubts, although I knew, because every scientist thinks their science is really important. Turns out theirs is. And I realized later that they were largely responsible for the Cassini mission getting conceived. So I realized that they really knew a lot about why we should do things, and so I started looking more carefully. And that's basically how that experiment then had to go through a long, painstaking process of convincing my colleagues that knew about the hardware and the measurements that it could actually be done. A lot of people didn't think that we could figure out how to do this, but we kept pushing and kept working. And once we got that figured out, we then joined with the other teams that were already interested in doing Jupiter's gravity and magnetic fields, and then another team that was interested in doing the polar magnetosphere, and I put them all together under one umbrella, and NASA came out with an opportunity that could allow that kind of a mission, you know, at that level of expense and complexity. And so we all came in under one umbrella and proposed Juno, and that was back, I mean, the ideas were conceived maybe back in around 2000, 1999, when the water abundance idea came in, and it got added for the AO was about 2003, and so that's when the teams all came together, and so that's how long we've been working together.
So if I could just follow up, Jim Green, when you heard this, or your predecessor, what did you think?
Well, first off, Juno was selected when we came on board. This is Jim Green and myself, and we were given this mission, and we were immediately impressed with how well it was run, and the fact that it had spent some time in Phase B, and so it was ready to graduate. And so one of the first things that we did was we ran it through a confirmation review where we said, okay, no kidding, for sure, for real, is this science that we really want to do? Can we do it at the cost and on schedule that's been proposed, derived during the Phase B? And all of the answers came back unanimously yes. And so we said, this is compelling science, let's move forward. And we're very excited about it. It's going to tell us a lot about not just Jupiter, but I'm sure Scott's mentioned in some of the science briefings just about the solar system in general and how it was formed, and maybe even a little bit about how the Earth was formed. So we're very excited.
Any other questions? All right, we have, well, let's get Craig, because he's right here.
Thanks very much. It's Craig Kovalt with Aerospace America. For Jim Adams, a question relative to the decadal. Now that you've had some time, how do things stand with ESA on major issues on the decadal? Anything new there relative Mars, for example?
So the decadal survey is, for those that don't know, is a 10-year outlook of the science that ought to be pursued by planetary science from 2013 to 2023, essentially, or the end of 2022. We're in the process of mapping out our plan on how to respond to the decadal survey. And international partnerships, like in all of our missions, play a key role in that. It's not quite all firmed up yet, but we're working on that. What we're really excited about is the fact that Juno played a key role in the previous decadal survey and tells us a lot, answers a lot of the questions that were asked by the previous decadal survey. And so we're looking forward to doing that in the middle of this decade as we're working on responding and putting together missions that will respond to the next decadal survey.
Okay, we'll take one more question. This lady right in front, right here.
Jackie Goddard for the Times of London. This phrase, unlocking the mysteries of the universe, is one that folks like you use a lot in explaining stuff to us, and that we use a lot when we're writing our articles and whatever. In terms of this particular mission, how great a leap in understanding are we expecting? Is it going to be kind of inching our way along that scale of understanding, or are we expecting one giant leap?
Well, my belief is that we make progress by taking many small steps. And there are some great leaps that you get to do once in a rare while. But most of the progress we make as humans is we make small steps, and we just have to keep at it. You know, whether this is a giant leap or a small step maybe is somewhat judgment here, but I think that the real interest in Juno and Jupiter is that it's really giving us insight into the very earliest times of our solar system formation, right after the sun formed to the beginning of the planet, the first planet. And in that sense, it's a big leap, because that's a big step to take, to get that first step that goes from a sun or a star to the planets, because, you know, the planets are made of a little bit differently than the sun, or we wouldn't be here today. There is a difference there. We don't really understand how that happened, or what happened, and what the elements or volatiles were doing early in the solar system. And so that's a big step, a big leap. However, you know, I don't want to imply that other steps aren't equally important. I mean, I think that if we're going to understand nature and understand ourselves and our role and all of the planets, we need to keep looking at all the planets. We need to look at every body we can in the solar system and in the universe, and galaxies, stars, everything, and really try to understand how they're different and what role they play and how we fit in.
Todd?
Todd Halverson of Florida Today. I was just curious if any of you were conscious of the fact that you guys are the first post-shuttle era launch, and what your thoughts, if any, have been on that, and whether you really could kind of feel that. I certainly felt it today as that rocket was going up, and I think a lot of people around the center did. And I'm just wondering what your thoughts are on that.
That's a great question, and maybe all three of us could answer what we think about that. About 4 months ago, I was in an elevator with Charlie Bolden, and I said, you know, Juno is the first launch after the last shuttle, and we need to find a way to engage the people that are going to feel that loss. And so I said, you know, normally we invite 300 to 1,000 people out to an expendable launch vehicle launch, I said, Charlie, what do you think about inviting 10,000 people? And he said, that's a great idea. Let's figure out how to make that happen. And I immediately backed away, and I said, oh, well, I don't know if I could do 10,000, maybe 5,000. He said, if you don't try, then you won't make it. And latest estimates were that we beat the 10,000, not just invitees, but actual people that watched. And we're extremely excited about coupling the energy that the nation has with regard to human spaceflight into understanding what we're doing in science. Because right now, science is really the positive face of this agency. We're looking very forward to what we can tell the world about what we're doing in planetary science. And stick around. It's going to be a great year. We've got GRAIL and MSL coming up, and it's just going to be fantastic. You guys have comments on that?
Well, I mean, it was exciting. It's sort of a privilege, I feel, to be in that transition spot and have the attention and the spotlight that comes with that. We didn't plan this. When we were figuring out when to launch, we were just trying to figure out, when are we going to finish, and where's Jupiter, and where's Earth, and how do we get there? And we picked our launch date, and or I should say, the launch date picked us. And then the shuttle program started to wind down, and of course, the exact last shuttle danced around a little bit, and we ended up falling on that right where it is. I have a great respect for the human spaceflight program and the shuttle program. I think they achieved incredible things, and so I'm honored to be in this transition, trying to help out a little bit. I think you're right. There's people that feel a loss, and there's also the public that needs to understand that the NASA's more than about the shuttle. It's really about exploration in general and just reaching out, trying to understand and reach ourselves both physically as humans out to the stars. When I was a kid, I used to look up, from these dark fields and feel myself hurtling through space on this planet, kind of on a rock. I'm hurtling through this three-dimensional star field. I used to imagine this. Of course, I watched Star Trek too. And I think that reaching out there, trying to get out there, is very important. So I really love the shuttle program and the Apollo program that came before that. But we're in this magical period, and we need to make sure that everybody realizes that NASA also reaches out to understand nature with science, and this is a platform to emphasize that to people. And so I think that we're fortunate that to be here, and Juno, fortunately, is sort of an exciting, fundamental mission that can carry that kind of thing forward. Jan, you may have your own views.
I would just I agree with what Jim and Scott said, and I guess I would just like to add that it's serendipitous that we are the first mission to launch in the post-shuttle era, and I'd like to think that the excitement that the human spaceflight program has generated in the American and world population will carry over to the planetary scientific missions a little more than it used to. As Jim pointed out, it's unusual to get 10,000 people at a planetary launch, an unmanned launch, and so I'm just happy for the opportunity to publicize the great science that we're doing, and maybe we're getting some of that because we're riding on the coattails of the excitement and emotion of the last shuttle launch.
All right, that's going to conclude our launch coverage today. And we're going to close out now with a replay of the launch from earlier this afternoon. Thank you very much. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
Pitching our roll program is in progress. Vehicle body rates look good. Booster PU has gone to fixed angle, surely confirmed. SRB chamber pressures have plateaued. I'm rolling off. Signatures look good. RD-180 operation looks excellent at this point in the flight. Mach 1. SRB chambers continue to roll off. Max Q.